cosmology. Physical cosmology, as a branch of astronomy, is the study of the largest-scale structures and dynamics of the universe, and is concerned with fundamental questions about its formation and evolution.
The WMAP science team defines cosmology as the scientific study of the large-scale properties of the universe as a whole, using the scientific method to understand the origin, evolution, and ultimate fate of the entire universe. To employ the scientific method, we need a way to observe the universe's large-scale structure, since our understanding of the universe depends heavily on our ability to observe it directly. Not long ago, great astronomers like Harlow Shapley believed the entirety of our universe to be within our Milky Way galaxy. Hubble's detection of novae in the Andromeda galaxy around the 1920s was instrumental in ending the great debate of whether or not galaxies like our own existed outside the Milky Way. Similarly, observations of distant galaxies today allow us to get a map or a better understanding of how galaxies must be distributed in space. They also allow us to test the robustness of such cosmological models such as the Lambda CDM. Galaxies, being the unit marker of matter distribution in cosmology, and their distribution helps us to understand the canvas they are on even better. The source counts distribution of radio sources from radio astronomy surveys shows the distribution of the number of sources in a given brightness range. Generally, brighter sources were easier to study in the past, so fainter sources were not as extensively understood as brighter sources are. But today, with such technological advances as the extended VLA, we are able to push the limit further on how faint we can study galaxies. The Very Large Array has 4 different configurations, A, B, C, and D, which return images with different sensitivities. I will use data from the B and C configurations to get an image with some sources. I will simulate a random uniform source distribution and run the 2-point correlation function code on it. I will also run the 2-point correlation function on the B and C configuration data from the VLA. On the left hand side is the radio image, and on the right hand side the sensitivity image. The central parts of the radio image contain the region of maximum sensitivity as shown in the sensitivity image on the right. This affects the appearance of the sources on the radio image by distorting them. Therefore, corrections need to be made to account for the fact that sources closer to the center are favored. The special 2-point correlation function describes the distribution of galaxies in the universe. One picks a galaxy randomly from the data, draws a circle of radius r around it, and calculates the probability of finding other galaxies within the circle bound by that radius in space. Varying the extent of the radius r gives an indication of the lumpiness as a function of scale of matter in space. The results should be different, as we expect that sources exist in groups, clusters, etc., and that space is lumpy rather than smooth in terms of galaxy distribution.